The expanding universe and the stardust within, the saga of Betelgeuse ***. In 1929, a monumental shift reshaped humanity's understanding of the cosmos. Scientists discovered that the universe, long thought to be a static, unchanging expanse, was in fact expanding. This revelation, one of the most profound in the history of astronomy, altered how we perceive our place in the grand tapestry of existence. The breakthrough stemmed from meticulous observations of Edwin Hubble, an American astronomer whose work with distant galaxies unveiled a universe in motion. His findings laid the cornerstone for the Big Bang Theory, a model that describes a universe's origin as a rapid expansion from a single, dense point billions of years ago. This discovery opened the floodgates to a century of scientific advancements, revealing the dynamic nature of the cosmos and connecting the lives of stars to the very elements that form our bodies. Today, as technology advances, astronomers have turned their gaze to Betelgeuse, a massive red supergiant in the Orion constellation, whose erratic behavior hints at its potential demise in a spectacular supernova. This star, a beacon of cosmic evolution, offers a real-time window into the life and death of stellar giants, reminding us that we are, quite literally, made of stardust. The dawn of a new cosmic perspective. The early 20th century was a time of rapid progress in astronomy, yet the prevailing view held that the universe was eternal and unchanging, a fixed stage upon which galaxies, stars, and planets played their roles. This static model, rooted in centuries of philosophical and scientific thought, was challenged by Edwin Hubble's groundbreaking observations at the Mount Wilson Observatory in California. Using the 100-inch Hooker telescope, then the largest in the world, Hubble studied distant galaxies, observing their light through a technique known as spectroscopy. He noticed something extraordinary. The light from these galaxies was redshifted, meaning its wavelengths were stretched, shifting toward the red end of the spectrum. This redshift, a manifestation of the Doppler effect, indicated that these galaxies were moving away from Earth. Hubble's observations, published in 1929, revealed a pattern. The farther a galaxy was from us, the faster it appeared to recede. This relationship, now known as Hubble's law, provided compelling evidence that the universe was expanding in all directions. The implications were staggering. If the universe was growing, it suggested a beginning, a moment when all matter and energy were concentrated in an infinitesimally small point. This idea gave rise to the Big Bang Theory, formalized in the decades that followed by scientists like George Lemaitre, who had earlier proposed an expanding universe model, and others who refined it with mathematical precision. Hubble's discovery shattered the static view of the cosmos, replacing it with a dynamic, evolving universe, one that had a history and a trajectory. The impact of this revelation extended beyond astronomy, touching philosophy, theology, and our collective sense of identity. If the universe had a beginning, what caused it? How would it evolve? These questions spurred a cascade of research throughout the 20th century, as scientists sought to understand the forces shaping galaxies, stars, and planets. By 1957, the cosmic picture had grown even clearer. Researchers recognized that the sky was not a mere decorative canopy, a fixed backdrop to human existence, but vibrant, evolving landscape. Galaxies collided and merged, stars were born and died, and the universe itself was a theater of constant change, driven by gravity, nuclear fusion, and other fundamental forces. Stardust, the cosmic alchemy of life. One of the most profound insights in this era of discovery was the realization that the elements composing our world and our very bodies originated not on Earth, but in the fiery hearts of stars. The hydrogen and helium that dominated the early universe formed in the aftermath of the Big Bang, were the raw materials for stellar birth. Within the cores of stars, intense heat and pressure triggered nuclear fusion, a process where atomic nuclei combine to form heavier elements. Hydrogen fused into helium, releasing energy that powered the star's brilliance. Over millions or billions of years, depending on a star's mass, this fusion progressed, creating carbon, oxygen, nitrogen, and eventually heavier elements like iron, calcium, and beyond. For massive stars, the journey doesn't end with fusion alone. As they exhaust their fuel, their cores collapse under gravity's relentless pull, triggering catastrophic explosions known as supernovae. These violent events scatter the star's outer layers, rich with newly forged elements, into the interstellar medium. The iron coursing through our blood, the calcium strengthening our bones, the carbon forming the basis of life. All were born in these stellar crucibles. This process, often called cosmic alchemy, links the lives of stars to our own existence. We are, in a poetic and literal sense, made of stardust, a product of the universe's relentless cycle of creation and destruction. This cycle is not merely a historical footnote. It continues to shape the cosmos. Supernovae enrich gas clouds with heavy elements, which collapse under gravity to form new stars and planets. Earth itself, and the life it harbors, owes its existence to these ancient stellar explosions. The realization that we are connected to the stars, that the building blocks of our bodies were forged in cosmic furnaces, underscores the unity of the universe. It bridges a vast gulf between the microscopic and the cosmic, revealing profound interdependence between the smallest atoms and the largest structures in existence. Betelgeuse, a star under scrutiny. As our understanding of the universe has deepened, technological advancements have allowed astronomers to study individual stars with unprecedented precision. Among the most captivating is Betelgeuse, a red supergiant in the Orion constellation, visible to the naked eye as a faint reddish point of light. Historically, Betelgeuse has ranked among the brightest objects in the night sky, drawing the curiosity of stargazers and professional astronomers alike. Its name, derived from the Arabic Yad al-Jawza, meaning the hand of Orion, reflects its prominent position in one of the most recognizable constellations. Yet, in recent years, Betelgeuse has captured global attention not for its steady glow, but for its erratic and unpredictable behavior. Betelgeuse is no ordinary star. With a mass estimated at 15 to 20 times that of our Sun, it is among the largest and most luminous stars known. If placed at the center of our solar system, its outer layers will extend beyond the orbit of Jupiter, engulfing Mercury, Venus, Earth, and Mars. Despite its immense size, its surface temperature is relatively cool, around 3,500 Kelvin, compared to the Sun's 5,500 Kelvin. This cooler temperature, a hallmark of red supergiants, results in a reddish hue and a lower energy output per square meter, which tempers its brightness despite its vast scale. Located approximately 640 light-years from Earth, Betelgeuse is close in cosmic terms, yet still far beyond the reach of current technology. A journey at the speed of light would take 640 years. With today's propulsion systems, it would take millions. The star's recent behavior has sparked intense scientific interest. Betelgeuse has long been classified as a pulsating variable star, meaning it undergoes natural cycles of expansion and contraction that affect its brightness. When it expands, its surface area increases, and it shines more brightly. When it contracts, it dims. Astronomers have identified at least two dominant cycles, one lasting about 185 days, and another spanning roughly 2,300 days. These pulsations are driven by internal processes, including the fusion of heavier elements in the star's core and outer shells. However, in recent years, the severity and unpredictability of these changes have raised eyebrows. The Great Dimming and Supernova speculation. One event, in particular, galvanized the astronomical community: the Great Dimming of early 2020. During this period, Betelgeuse's brightness plummeted to a magnitude of approximately 1.61, a significant departure from its typical range of 0.2 to 1.2, where lower numbers indicate greater brightness. This dramatic fade, the most pronounced in decades, sparked widespread speculation that Betelgeuse might be on the brink of a supernova explosion, a cataclysmic end to its life. The star's reddish appearance, a result of its cool surface, and its massive size already hinted at its advanced age, but the Great Dimming intensified the debate. To understand these changes, astronomers employ a suite of tools. Photometry, the measurement of a star's brightness over time, tracks fluctuations in light output. Spectroscopy, which breaks light into its component wavelengths, reveals critical details about surface temperature, elemental composition, and the motion of the star's outer layers. Advanced computer models, incorporating complex equations of stellar structure and nuclear fusion, simulate the processes unfolding within Betelgeuse. These tools have shed light on the possible causes of its erratic behavior, pointing to a combination of internal and external factors. One key process is convection, where hot material from deep within the star rises to the surface, while cooler material sinks. These convective currents, some larger than Earth itself, transport energy and influence brightness. Variations in the efficiency of this heat transport can lead to noticeable shifts in light output. Additionally, Betelgeuse sheds mass through powerful stellar winds, expelling material into space. This ejected material can form dust clouds, which temporarily obscure the star's light, creating a dimming effect that may not reflect an actual drop in energy output. During the Great Dimming, some researchers propose that a large dust cloud, formed from this ejected material, contributed to the observed fade. Another possibility lies in the star's internal fusion processes. As a red supergiant, Betelgeuse has exhausted the hydrogen in its core and now fuses helium into carbon and oxygen in its outer shells. These reactions send waves of energy through the star, causing it to expand, contract, and pulsate in a rhythmic pattern, sometimes called the star's heartbeat. Disruptions in this rhythm, driven by changes in fusion or convection, could explain the recent fluctuations. Scientists have also considered the possibility of a hidden companion star. In binary systems, stars orbit each other, sometimes exchanging mass in ways that alter their evolution. While no definitive evidence of companion has been found, the theory remains a tantalizing possibility, prompting further observation and analysis. The supernova scenario, a cosmic spectacle. The most dramatic and captivating scenario is that Betelgeuse is nearing the end of its life, poised to explode in a supernova. Massive stars like Betelgeuse live fast and die young, burning through their fuel in millions of years rather than the billions enjoyed by smaller stars like the Sun throughout its life. Betelgeuse has maintained a delicate balance between the outward pressure of fusion and the inward pull of gravity. As it fuses heavier elements, helium to carbon, carbon to oxygen, and eventually oxygen to iron, this balance becomes precarious. When the core begins producing iron, fusion no longer generates energy to counteract gravity. In a matter of seconds, the core collapses, triggering a violent explosion that ejects the star's outer layers into space. A supernova from Betelgeuse would be a celestial event of extraordinary magnitude. Its brightness could rival that of the full moon, making it visible during the daytime for weeks or even months. It would become the most luminous object in the night sky, a testament to the raw power of stellar death. Fortunately, at 640 light-years away, Betelgeuse poses no threat to Earth. A supernova at this distance would be a spectacle, not a danger. However, if such an event occurred closer, within a few dozen light-years, the consequences could be severe. Gamma-ray bursts, sometimes associated with supernovae, could strip away Earth's ozone layer, exposing life to harmful ultraviolet radiation. This could disrupt ecosystems, harm human health, and damage agriculture. An electromagnetic pulse from a nearby explosion might also interfere with satellites and electronic systems. After the explosion, Betelgeuse's core would collapse into a remnant, either a neutron star, a dense city-sized object composed mostly of neutrons, or, if the mass is sufficient, a black hole. A black hole at 640 light-years would pose no risk to Earth, but would offer a unique laboratory for studying extreme physics. Material spiraling into a black hole emits intense radiation, providing insights into gravity, high-energy astrophysics, and the nature of space-time itself. Whether Betelgeuse becomes a neutron star or a black hole, its fate will mark the end of one's stellar life and the beginning of a new chapter in cosmic evolution, the legacy of stellar death and rebirth. Supernovae are not merely dramatic endings. They are also crucial beginnings. The explosion of a star like Betelgeuse would scatter heavy elements, carbon, oxygen, iron, and more, into the interstellar medium, enriching gas clouds that will one day collapse to form new stars and planets. This cycle of death and rebirth is the engine of cosmic evolution, driving the creation of the building blocks for future solar systems. The elements forged in Betelgeuse's core could one day form the basis for new worlds, perhaps even nurturing life as we know it. Should Betelgeuse go supernova in our lifetime, it would be a rare and extraordinary event, a vivid demonstration of the universe's dynamic nature. Predicting exactly when this might happen is challenging. Betelgeuse is in the final stages of its life, but final in stellar terms could mean tomorrow, a century, or 1,000 years from now. The great dimming and other fluctuations have heightened interest, but astronomers caution that these changes could be part of natural cycles rather than a definitive sign of an imminent explosion. Observatories worldwide, from ground-based telescopes to space-based instruments like the Hubble Space Telescope and the James Webb Space Telescope, continue to monitor Betelgeuse, collecting data to refine models and predictions. A window into the universe's story. The story of Betelgeuse, like the discovery of the expanding universe, underscores the ever-changing nature of the cosmos. Edwin Hubble's 1929 breakthrough revealed a universe in motion, expanding and evolving over billions of years. The realization that we are made of stardust, forged in the hearts of ancient stars.